Okay, let's continue our discussion. Okay.
Okay.
Today we will finally discuss the long-awaited affine transformations.
Okay.
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 Let me share my board. Okay. Before sharing my board, affine transformations are just a change of coordinates. Okay.
Okay.
We have studied affine transformations in various contexts, especially in physics, where we change the system from one coordinate to another coordinate.
Like an spherical polar, like that?
Those are transformations, but affine transformation has to preserve certain geometric conditions. Okay.
Okay. So like in when we transform a vector from, let's say,
for instance, a
rectangular coordinate system to spherical polar coordinate system.
No, okay, that is also transformation. Affine transformation is more like a rotation or reflection.
Okay, so yeah, so in rotation and reflection, the length of the vector should be.
Okay, length may change, but continuity will never break.
Okay.
Okay. We are studying algebraic geometry, especially algebraic geometry of curves, isn't it?
Yes.
Okay. So we are not talking about like vectors here. We are talking about algebraic curves.
Okay.
Okay. So in algebraic curve theory, we are more concerned with things like continuity. Okay. Let's say we have a curve, and if we perform a change of coordinates or if we perform a transformation, if the continuity of the curve breaks, then that is not an affine transformation.
Okay, let's come to that.
Okay. Also, parallel lines should always remain parallel. That's very important in affine transformation. Okay. Parallel lines will always remain parallel. But when it comes to projective geometry, parallel lines may not remain parallel. Parallel lines may intersect. That is very, very interesting. That we will study when we look at projective geometry.
Okay.
Okay. Today we shall discuss affine transformations. Let me share my board. Okay. Can you see the board, Jeff?
Yes.
Okay. Let me write a heading here. Real affine transformation. Or just a change of coordinates. Affine transformation or affine change of coordinates. Change of coordinates. Okay, Jeff.
Okay.
By real, we mean we have earlier in the first class we have said that. Let me take the first page of our discussion. Okay. Here, what is this here?
Exactly. All the values are, all the coordinates or all the values are actually members of real. We are only looking at the real plane.
They are real numbers because since we are dealing with the conics in the real plane.
Yes. Okay?
Let's say we are first discussing real affine transformation. Later we will discuss complex affine transformation. It's very, very interesting. Okay. Okay, let me draw a coordinate system here. This is a coordinate system. Okay.
Okay.
Let's assume there is a circle in this coordinate system.
Okay.
Yeah. Let this be a circle.
Okay.
This is x and this is y. Okay. So this is x. This is the xy plane.
Okay.
Okay. Let the center of that circle lie at the point AD. Okay.
Okay. 1 second.
Meaning this point is A, comma B. The center of that circle is A, comma B. AD.
Okay.
Okay. A, comma B. Okay. Now let's perform. Let's move this coordinate system so that okay, let's move this circle, let's transform this circle to a new coordinate system such that in that new coordinate system, the center of its circle is at the origin.
Okay.
Okay, let me move the center thing to the center here. Okay, meaning we are going to define a new coordinate system here. Okay.
Okay.
Let me name this new coordinate system UV. Okay.
Okay.
In the original coordinate system, see, let's say this is O and this is O dash. Okay. This
Okay.
origin be O dash. O dash. Okay. In the original coordinate system, a point in the circle was denoted by the coordinates xy. Isn't it?
Yes.
This is xy.
Mm,
But in the new coordinate system, that point will be transformed to
UV or
UV. Yes, UV. Because
okay.
here the coordinates are named as U and V. Okay. So we want to find the transformation.
Okay.
Now, okay, we know that this distance is A. Isn't it, Joe? A.
Uh,
And this distance is B because this is point B. This distance is B.
yes.
Okay.
Okay.
So we can write the transformation equations as A plus U becomes X. Right? Because this
Yes.
distance is U. This distance is U. And this
Okay.
distance is V.
Okay.
Let me zoom in and show you. Okay. Can you see?
Okay, let me just wrap my head around it. So you will have okay, 1 second. Oh, okay. It's okay. That's all right.
Okay.
Okay.
In our
So
original coordinate system O, this point was xy. In our new coordinate system, this point is UV because
yeah.
every point in that circle is now denoted as U and V. Okay. Since this point
Okay.
is taken, the x coordinate is U and the y coordinate distance from the origin is origin in the x coordinate is U and the distance from the origin in the y coordinate is V.
Okay.
Okay. So we can write the transformation equations are
1 second. So exactly. So let me recap what you have said. So we are taking a new coordinate system with UV at the center of the old of our circle. So our point. So if you define a point, let's say P in on the circle, then it will be represented as some arbitrary x comma y or ordered pair x comma y in our old coordinate system, while it is defined as UV in our new coordinate system. Am I right?
yes.
Okay. Okay. Okay.
Okay, now we shall find the transformation equation,
Okay.
which is just a plus u equals x, isn't it?
Okay.
Because this distance is u, this is u from here to here.
Okay. 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 I'm
So
getting
let
the
me
idea.
zoom and show you.
I'm getting the idea now.
Okay, this distance is u. This distance was a. This is a.
Okay.
A plus u will be the x coordinate. X. This is x. Right?
Oh, yeah. This must be A and this must be A and this must be B, and this much distance will be U. Okay. In the old coordinate system and x, y in the new coordinate system. So we can say u x is equal to u plus a and y is equal to v plus b. Am I correct?
What? X equals u plus and y equals yes. Y equals in this y coordinates we can write b plus b equals b plus v
Equal to y.
equals y. B plus v equals y. So you can write u equals x minus a and v equals y minus b. Right, Jay?
Yeah.
So this is our Affine transformation. This is our Affine transformation. From the initial coordinate system xy, we obtain the new coordinate system uv. This is a transformation from x comma y to u comma v, which is just a translation of the origin. We just change the. This is change of origin.
Okay.
Okay.
Okay. So what makes this an affine transformation? Why do we call this an affine transformation?
Because it doesn't alter the continuity of the code. It is just a change of the origin. That's what I initially said. Affine transformation never breaks the continuity. The circle will never become a parabola. Okay.
Okay.
Okay. Because in parabola, the circle has to open. Isn't it? It has to become like this. That will never happen in an affine transformation.
Okay. Okay.
Okay, John?
1 second. Okay. 1 second. 1 second.
Okay, take your time. Take your time.
Okay. Could you zoom out? It will be better.
Zoom out.
Yeah.
Huh?
No. It's okay. You can zoom in. Okay.
Okay. Okay, John.
Yeah.
Okay, this is what affine transformations are. Okay, this is a particular example of an affine transformation. This is change of origin. Okay. This is change of origin. Okay.
Okay. So affine transformations preserves the continuity of the curve, isn't it?
Okay. Yes. It also preserves parallelism, but we are not concerned with parallelism here because we are not dealing with the parallel line. We are studying conic sections. Okay. Now the most important thing here is that origin is not relevant here because in an affine space, affine space is a space in which we can perform an affine transformation.
Okay.
Okay. Here we are dealing with the two-dimensional affine space, also known as the affine plane, A2.
Okay.
Okay, A2. Okay. In an affine plane, the origin is not relevant because we can make any point the origin by finding a suitable affine transformation.
Okay. So okay. So affine plane or a space is a space or a plane where affine transformation is possible, isn't it?
Okay. Okay.
Any point can be made in origin by using affine transformation, isn't it?
By finding a suitable affine transformation. Here, the origin is the origin is just another point. Okay, we can always find a suitable affine map to make any point as the origin. Okay.
Okay.
So we are dealing with affine plane A2. An important consequence of this transformation is the equations of the conic can be altered in form. That's very important. For instance, let's this circle. This is a circle, isn't it, Joe?
Yeah.
Okay. So let's find the write the equation of that circle in the xy plane. Equation of this circle in the xy plane. XY plane. What is it, Joe?
Equations of the circle, the xy plane is.
This
Okay.
equation of this circle in the this is centered at AB. So what will be the equation? Okay. With this, let's assume it has a radius R.
Okay.
So what will be the equation?
X minus a the whole square.
X minus a whole square
Plus y minus b the whole square is
y
equal
minus b whole square equals
r square.
Okay, expand this each of this term.
One second. R is the radius of circle.
Yes, exactly.
So that will be x square plus a square plus y square plus b square minus 2ax minus 2ay minus r square is equal to 0.
Exactly. So let's rearrange to obtain x squared plus y squared minus 2ax minus 2ay plus a squared plus b squared minus r squared equals 0.
Okay, 2ax minus 2ay minus a square plus a square plus b square minus r square is equal to 0. Okay.
Okay. On comparing with the origin with the general equation of conic. Okay. The general equation of the conic is what's the general equation of the conic? Do you remember?
Ax square plus by square.
Exactly. Equation of conic is ax squared plus bxy plus cy squared plus dx plus ey plus h equals 0, isn't it?
Yes.
So we obtain a equals, what are the coefficients? A equals,
one second. A will be equal to here. A will be equal to 1. B will C will be equal to 1.
B will be
0.
B will be 0. That's very important actually.
Okay.
We will return to that idea in the next class. Okay. A equals 1, B equals 0, C equals
Z equals 1. Okay, let's
D equals.
Okay, one second, man. It's better to write this in take these terms as some k h some other terms, because we may confuse these two small these a's centers.
Okay, just write it. Okay, it doesn't matter. Just write. D will be.
Okay, one second.
I'm just writing this to explain certain idea. Just write. It doesn't matter. Okay, D equals.
Yeah. One second. C is equal to 0 and
C equals 1.
C is equal to 1. D is equal to negative 2a.
D equal to minus 2a. Okay, then E becomes
E equal to negative 2b.
2b exactly. I have made a mistake here. This is B.
Yeah, me too.
2b. Okay. 2b And what is h?
H is equal to h will be equal to a plus b plus a square
A
plus
squared plus b squared minus r squared.
yeah.
Okay. This is the equation of the conic in the xy plane. Now,
Yes.
what will be the transformed equation?
Okay.
What will be equation of the same conic in the UV plane, UV coordinate system?
Conic in UV coordinate system. UV coordinate system. So that will be equal to, if you write u square plus v square should be equal to r squared.
Okay, when we compare to our general equation of a conic, what is A? Here A is,
When comparing to general equation, A will be equal to 1. Okay.
A will
B,
be 1,
B equal to 0.
B equals 0,
C is equal to 1.
C equals 1.
Am I right?
Yes, yes.
C equal to 1. D will be equal to 0. E will be equal to 0. H will be equal to R negative R square.
Yes, exactly. Okay. That means performing an affine transformations changes the entire form of that equation. Not form, but the coefficients of the general quadratic equation.
Okay.
Okay.
Affine transformation changes the coefficient
of that general quadratic equation. That is performing an affine map changes
the coefficient of
the equation of the conic. This is very important because let's say we have a very complicated equation. Okay.
We can use an affine transformation to make it simpler.
Exactly. That is a very important application of the affine transformation in pure mathematics. In computer science, digital image processing, and graphics algorithms, the affine transformations are used throughout in every aspect of those systems. But this is one of the application in pure mathematics because we can transform the equation so that the form becomes simpler.
Okay.
Okay, that is one of the utilities of affine transformation. Okay. Okay, let's move on from change of origin to discussing about rotations. Okay, rotations are also affine transformations. I will give you the general form, but let's look at some examples.
Okay.
Rotation. Okay, Joe, before doing that, let's look at the transformation equations one more. Okay, this is the affine transformation. These are the affine transformation equations, right?
Yes.
Let me rewrite that equation here. U becomes
x minus a,
and V becomes
y minus b.
y minus b. Okay. Can you convert this into a matrix equation?
Yeah, I think so.
Okay, we can convert this as u v equals x. So it will become 1 0 0 1 times x y plus minus a minus b. Isn't it?
Yeah.
Okay, Jim.
Yeah.
because when we multiply this identity matrix with xy, it just becomes xy.
Okay.
It becomes a vector xy plus the vector minus a minus b. It will result in uv equals x minus a and x minus b. And when equating, we obtain the origin. Okay. Okay, Joe.
Let me just check. Okay, write it. Okay.
This is the matrix of this Affine transformation. Okay. Matrix form.
Okay.
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 This is just explicit form of just polynomial representation. Okay. Okay. Now let's move on to discussing rotations.
Okay.
Rotations. Let's say we have a coordinate here, coordinate system here. This is a coordinate system, and we want to perform a rotation, say like rotate in an angle theta. Okay. Let's say this is the coordinate system is rotated in an angle theta.
Okay.
Okay. So this is x and this is y. Then this is the new coordinate system u and v. Okay, which is obtained by performing a rotation. Okay.
Okay.
If you remember, Joe, the rotation matrix is given by for a rotation theta. It is given by cos theta minus sin theta, cos theta. This is the rotation matrix. And multiplied with the xy will give you the changed code. Let me check. Yes. Cos theta minus sin theta, cos theta. For instance, let's perform an easy rotation of pi by 2. Okay. Okay.
Okay.
Okay. For theta, when theta becomes 90 degrees for pi by 2 radian, we will cos 90 becomes cos pi by 2 becomes 0, right? 0 sin pi by 2 becomes 1, so this will be minus 1. Then sin pi by 2 will be 1 and cos pi by 2 will be 0. And multiplied with the x and y, we obtain minus y and x. This will result in minus y and x.
Okay, 1 second. Yeah, 1 second. Cos theta. Yeah.
Okay, let's draw it and I don't know. Let's put a point. Let's put a point on that will explain this. Let's put x. Let's pick a point in the x-axis. 1 0. Okay.
Okay.
When you substitute here 0 minus 1 1 0 multiplied with 1 0, what will be the answer? 0 and 1. Okay. Okay, Joe.
Yeah, 1 second. Let me. Cos pi by 2 will be 0, negative 1. Sin pi by 2, sin is 1, 0. Yeah, it will be times x1. So our x dash will be negative y, and y dash will be x, isn't it?
Okay.
Yeah.
Okay, I have put values for x and y. I have chosen a coordinate 1 comma 0, and I have multiplied with our transformation matrix and obtain a new coordinate, new point. Okay. Let's plot those points. Okay. So our first point was in the x in here 1 comma 0, and our new point is 0 1.
Yeah.
Meaning this is here.
0 negative.
0 1. Multiply this two.
Yeah, 0 1.
0 1. Okay. So this will become This will be here 0, 1. This is just a 90-degree rotation.
Yeah.
Okay. 90 degrees. Okay. This is an example of a change of coordinates by rotation.
Yes.
Okay. So in general, an affine rotate and change of coordinates rotation will look like u v equals cos theta minus sin theta and cos theta times xy.
Yeah.
Okay.
Yeah.
This has some similarity with this equation, isn't it?
Yes. Yes.
Okay. Because here this is the rotation matrix is actually this identity matrix here, because here the rotation never took place. So in the place of rotation matrix, it is just identity matrix. There is no change in
Rotation
the
by
angle.
zero. Rotation with
Exactly.
zero.
Okay. Okay. Now,
Yeah.
but there is translation in x and y. That
Yeah.
translation is actually given by this part. Okay.
Okay.
Okay. Are you getting the picture is becoming more and more clear? The form is becoming more and more clear, isn't it?
Yes.
Okay. And finally, we shall discuss another important kind of affine transformations called that's very important. It's like a stretching. Stretching. Let me name it stretching. Okay.
Stretching
This
as
is elongating an axis or in both axes. For instance, let's say we have let's say this is our xy coordinate system. Okay. And I am plotting the units as 1, 2, 3, 4, and 1, 2, 3, 4. Okay. And let's perform an affine map to another coordinate system such that the ones in a unit is actually elongated by 2.
okay.
Okay. Now here the one is this much. Okay. Here this was 1, but now this is 1.
Okay.
And this is 2. And this is 3. So 2 units in the xy coordinate system is just 1 unit in the UV coordinate system.
Okay.
UV coordinate system.
Okay.
Okay. If you want to change the y coordinates also, we can perform a change of scale. This is more apt name is scaling. Okay. Stretching is just a naive. It's a naive name. Naive term. Okay. Let's say we are stretching this also.
Okay.
Like 3. 1 unit here is 3 unit here, maybe. I don't
Okay.
know. Okay. This is the one here.
Okay, so it must be, so the transformation matrix will
The
be
transformation matrix must be just multiplying the
multiply okay, yeah, so uv will be equal to x into or some alpha into xy.
Yes, u will be 2 times x and v will be 3 times y.
So 2 times I into xy.
2 times?
I into xy. I means identity matrix.
2 times I into.
Okay.
This is just we can just write it as u v equals 2x 2y. Okay, multiplying with an identity, we cannot.
Okay.
Can just write an identity here, but it doesn't make any change.
Okay. So this is 3 times. The x-axis is stretched 3 times, 2 times, and y-axis is stretched 3 times, isn't it?
Okay, so exactly.
Okay.
Okay.
Okay,
This
so
is also an affine transformation. Why? Because this also never breaks the continuity of a curve. A curve here will look like this, but it will never break the continuity. It may look like this because it becomes stretched.
Okay. So 3y. Should we can we write it as 2003?
2
003.
Yes, we can write it as 2003.
So this will
xy. Okay, this is also a transformation because when you multiply, we get 2x plus 0 and 0 plus 3y. Okay?
Yeah. So we have a general form, isn't it? A transformation matrix
Exactly.
multiplied by some.
Also, we can combine both affine transformations. For instance, we can scale and then perform a translation.
Okay.
Okay, for instance, you can this can be 2003 times xy plus some 5 6. Okay, this will look like a coordinate system here and a stretched coordinate system with origin at 5 5 6 or something. Okay. A circle will be, for instance, if we have an ellipse, it will be, after stretching, it will be a circle. Okay. That is, ellipse and a circle can be transformed from one to other via affine transformation.
Okay, so in an affine
that we will prove algebraically. Let's not go deep into that. We will prove that algebraically.
So we can say that a circle and a ellipse are equivalent in an affine space.
But we haven't shown that affine transformations are equivalence relations. That we will do today. But let's have you understood the concept here?
Yeah.
Okay. So a general affine transformation, a general real affine transformation is of the form u v equals a b c d times x y plus e f. This is the general form. Okay. And when we multiply these matrices and write it explicitly, we obtain u becomes ax plus by plus e, and v becomes cx plus dy plus f.
Okay.
This is the affine transformation. Affine transformation. Okay, this is the general affine transformation. Okay, Jay.
Okay.
Okay, I'm thinking about what shall we discuss later. Okay. Now let's move on to viewing affine transformations as equivalence relations. Okay. Affine transformations as equivalence relations. Transformations as equivalence relations. For that, we must check 3 conditions. Do you remember?
Symmetry. Translative.
Transitive.
Transitive. And reflexive.
Exactly. Reflexive is being related to itself. Okay. being related to itself. That is an identity transformation.
Yes.
First, let's check the reflexivity.
Okay.
Reflexivity. Reflexivity. Okay, let's say we are like reflexivity is just an identity transformation.
Transformation.
Identity map. That is u equals x and v equals y. That's it.
Yes.
Can be written in matrix form as u v
equal
as 1
1
0
0 0 1
times
x y.
exactly. Okay, this shows that every coordinate system is we can perform an affine map to itself.
Yes.
Okay, so we have checked the first condition, reflexivity.
So for every coordinate, we can perform an affine transformation to itself.
Okay, there's also another term for affine transformation is called affinity.
Okay.
Every coordinate system has an affinity towards it.
Okay.
Okay. Now, secondly, we shall check symmetry. Okay.
Okay.
Symmetry. Symmetry means what is symmetry, Joe?
If A is related to B, then B should be related to A.
Exactly, meaning there should be an inverse transformation.
Yes.
Okay, let's say we have a change of coordinates for a transformation from xy to uv. We then should also find a transformation from uv to xy.
Okay.
Okay, inverse transformation. Okay.
Okay.
Okay, meaning let's say we have an affine transformation. Let's look at the general affine transformation. uv equals a b c d times xy plus ef, right?
Yeah.
Okay. Okay, Joe?
Yes.
If this transformation has an inverse, we should be able to convert this equation into a form where xy stands alone in the LHS, and we shall find some transformation with uv here.
Yes.
That means that if we have a uv, we can find the xy here.
Yes.
That is an inverse transformation. Okay, so how do we make xy alone in let's say the right side? We shall first move ef to the other side, right?
Okay. Yeah.
So we shall write a b c d times xy equals uv minus ef, isn't it?
Yeah. 1 second.
Finding the inverse map. Finding the inverse map. Okay. Now let us. How shall we make xy alone here?
We can take the inverse of the matrix AB.
Exactly, and multiply it on both sides.
Both sides.
That is, we shall find A, B, C, D inverse when multiplied with the A, B, C, D times xy equals A, B, C, D inverse into U, V minus EF. Isn't it?
Yeah. But the inverse should exist.
Exactly, that's the point. That's very, very crucial. If inverse doesn't exist, the transformation is not an affine transformation.
Okay.
So that's a crucial condition here.
So for affine transformation, when we write the general affine transformation, A, B, C, D is invertible, isn't it?
Exactly. It should be an invertible matrix. Okay. What is the inverse of a matrix? Do you remember?
Uh,
Okay,
yeah.
and the inverse of a matrix is actually, it can be found out by many different ways, but a standard way is finding
The
the determinant and then finding the adjoint
divided by
matrix. Exactly, adjoint divided by the determinant.
yes.
Okay, what is adjoint? Adjoint is actually transpose of the cofactor matrix.
Yes.
Transpose of the cofactor matrix. What is cofactor matrix? Elements of the cofactor matrix Cij can be found out as minus 1 raised to I plus j Mij, where Mij is the minor. This is elements of cofactor matrix.
Yes.
Element of cofactor matrix Cij is okay. Minor. What is minor? Minor is the determinant omitting the ith row and the jth column.
Okay.
Okay.
Yeah. We are.
Okay. There is also another way to find inverse by performing elementary row operations.
Yeah.
Okay. Essentially, both of these methods are essentially same.
Same, but when we do that,
let's do this. Let's find a determinant by this way. This is very easy here.
easy.
Okay. Okay. Let's find the minors here. The matrix A is A, B, C, D, isn't it?
Yeah.
So M11 will be omit the first row and the first column and find the determinant of this thing, which is just D.
D.
And M12 equals
will be C.
C, exactly. M21 will be
M21 will be B.
B, yes. Then M22 will be
A.
A. These are the minors.
Yes. So cofactors will be
Exactly.
C11 will be
minus 1 raised to 1 plus 1 M11. That will become
D. C1.
D, exactly D.
C1.
Then C12 becomes
negative C.
Minus C, negative C, correct. Then C21 will be negative B. Then C22 becomes
A.
Exactly. So we get the cofactor matrix as.
We can take that adjoint now, isn't it? Okay.
This is cofactor matrix. Cofactor matrix of this is cofactor. And this is adjoint. So we can we get the cofactor matrix as D minus C minus B and A. Okay. So we get the adjoint as, therefore adj will be the transpose of cofactor.
Yes.
Transpose of D minus C minus B and A. The transpose of this matrix. We just interchange the row and column. So we obtain D minus C and minus BA.
Yeah. Now we'll take the determinant.
Now let's find the determinant. That is the crucial thing.
AD minus BC.
Now determinant of equals A
D minus B.
AD minus what is
BC.
determinant?
AD minus BC.
AD minus BC, exactly. AD minus BC. And that determinant should never be
equal to 0.
If the determinant becomes 0, will an inverse exist?
No.
Exactly. So that this condition should be added to the definition of our affine transformation. Okay, this should never be equal to 0. That is very crucial. So when we talk about affine transformations, we should the symmetry of the affine transformation forces us this new condition.
Yeah.
Okay. So we should add this new condition, that is AD minus BC should not be equal to 0, to the definition of affine transformation. That is affine transformation becomes U equals AX plus BY plus E, and V equals CX plus DY plus F, with AD minus BC not equal to 0. Okay.
Okay.
This condition is very important, because to prove or disprove an affine transformations, we shall check this form. If this equation is in inequality, this not inequality, this term, if this is equal to 0, we can verify that this is not that transformation is not an affine transformation. Okay, Joe?
Yes.
So what will be our inverse? So therefore A inverse will be 1 by AD minus BC times the cofactor.
Yeah. So
D minus B minus C. D minus B minus C A. This is the inverse matrix. This is a completed definition. Okay.
Okay.
Okay, Joe. Have you wrote this equation? Have you wrote this equation?
Yes.
This one.
Yes.
Okay, so let's substitute that into this equation. Okay, we started solving this to find the inverse, right?
Yes.
So we shall multiply, substitute here to obtain x comma y equals 1 over AD minus BC times D minus B minus CA times UV minus EF.
No. Yeah.
Okay.
Okay.
Okay. Let's multiply it and find the explicit form. What is the explicit form? XY becomes 1 over AD minus BC. Let AD minus BC remain outside. Let's multiply this to obtain D minus B minus CA multiplied with UB minus D minus B minus CA multiplied with EF. Isn't it?
Yeah. Yeah, I'm there.
Okay, so we get 1 over AD minus BC times UD DU minus BV. This will be 2 by 2 matrix, correct?
Yeah. Yeah.
This will be 2 by 2 matrix. DU minus BV and minus CU plus AB minus another 2 by 2 matrix DE minus PF and minus CE plus AF.
Okay.
Okay. This is getting more complicated, isn't it? Okay, this is xy is here, right?
Yeah.
Okay. Okay, now let's just equate the
X and Y.
so x becomes 1 over AD minus BC times this term, right?
Yeah.
That's
du minus BV
minus dv minus again one, this becomes multiplied.
Yeah, you
here.
can take
Okay, AD minus BC.
common, isn't it?
Okay, you can write common also, doesn't matter. Multiplied with the dE minus BF. This is the equation for x.
Yeah.
Okay, and y becomes again 1 over AD minus BC times minus CU plus AV minus 1 over AD minus BC times minus CE plus AF. That's it. This
Yeah.
is it. Okay? This is the inverse map.
Yes.
Inverse transformation. Okay.
Okay.
This shows that finding inverse transformations are a bit complicated.
Yeah.
Okay, and the okay, look here. What is at the denominator here?
AD minus BC.
Yeah, exactly. That's why we wrote that condition explicitly here.
AD minus BC never equal to 0. Yeah.
Okay, it should never be equal to 0. Even not in the matrix form. Just when we write the explicitly find the inverse map, there also AD minus BC should never be 0. So that's the condition for a transformation to be an affine transformation.
Okay.
AD minus BC should never be equal to 0. Okay, Joe, let's conclude our discussion today.
Okay.
Because it's more than 1 hour, I think.
Yeah.
Okay. Okay. In the next class, we will finally look at the transitivity of affine transformation.
Okay.
Meaning, transitivity means xy is if xy is element of R and y is element of R, then x comma z should be an element of R. Okay.
Yeah.
That we will prove in the next class. Okay. Today we will just conclude here. Okay.